Thanks everyone. My name is Pierre-Yves. I'm currently the CTO at Exoscale. We're a Swiss cloud hosting company. I'm also an open source developer. Started a few projects, some in Clojure, such as Pithos Cyanide. I work with Riemann, the monitoring system that you might use. I hope you use it, and collect the. And today I'll talk a little bit about Mathematic. Since it's a programming language conference, I thought I'd give a few lines of background. I'm originally more of a C developer. I was a member of the OpenBSD team working on the network-related aspects and low-level kernel type stuff. And more recently, I had a rekindled interest in Lisp, and in a few companies I introduced and use mainly Clojure, which I'll talk about mostly today. The basic aim of the talk that I'm giving is to talk about distributed systems and why it might not be a great idea for you to design one from scratch, and to talk about two very specific aspects of the distributed system, which are allocation, resource allocation in a cluster. And how that can be a bit confusing and difficult to do on your own, and fault tolerance. And I won't speak about CAP because I think it's a subject that's been repeated over and over again. I might not be the best one to talk to you about that. So that's something, the compromises with regard to availability, partition tolerance, and consistency, that's something I won't talk about today. All right, so the outline of the talk is to start by reflecting a little bit on how we end up with a distributed system in the first place. Then talk about the primitives that Mesos can give you to make that a bit easier. And then we'll focus about how Clojure can help you make better decisions with regard to your distributed system. All right, so the first part is how do we end up with a distributed system? Because it's not an end in and of itself, right? That's not something that you set out to do. Most of the time, the time you start with a simple product idea. You want to change the world and disrupt the job board industry, for instance. But it's a simple idea, and you start off with a free tier standard application. It fits in like on a single box. Maybe it's a Clojure project, maybe it's a Java project, I don't know. And I don't think it falls within the usual definition of distributed systems. It looks like this. You have a simple HTTP service. It talks to a SQL database. It all fits on a single box. Life is good. And then you'll have, hopefully you'll have your first signs of success. Your single server doesn't service your needs anymore. You're going to have to span out to a few more instances. You figure out that your service is mostly stateless, your implementation, so you can span that to multiple machines, put a load balancer in front, and then you'll have your database that still sits there. Maybe you'll replicate it. One of the first things that becomes a bit harder is logging. When you want to have an insight into how things perform, you'll probably have to move to a centralized logging solution. So it looks like this. It still fits in everyone's head, and that's not what we usually refer to as a distributed system just yet. As the product grows and your service grows, you start adding features. You'll add subscription emails, but you can send those out in a synchronous manner from your main service. So you'll have to do that in asynchronous workers, which means that you'll also introduce a queuing mechanism, maybe RabbitMQ, maybe Redis, maybe Kafka, to add this. And at that point, most of the people start switching from a pet approach to machines to a cattle approach, which means they stop naming their machines with funny names, and then they start to reflect on their machines at homogeneous clusters of identical nodes. It does get a little bit more complicated. Your infrastructure starts looking like an actual infrastructure, and that's something that you tend to now, your infrastructure. And then the seed money runs out, right? So that's when you try and go for monetization techniques. At least that's not your idea. That's your CEO's idea. And so you go off with a freemium model with analytics, but that means that you have to actually run these analytic batch jobs. Everybody told you to use Hadoop or Spark, and I mean, where are you gonna run these batch jobs? And you partner with this company that has a very weird legacy system, but you need to exchange data with them, and they're like the only viable client library for their system is in PHP. That doesn't fit with the model you chose, Clojure. And where do you run this? And so your infrastructure is starting to get more and more involved. And as the product grows, your infrastructure grows as well. You have your whole CI pipeline that might be a bit complex and has like several Jenkins slaves to make sure you're always building efficiently. You split all your monitoring matters in different machines, and that's taking a large part of your infrastructure as well. You need a command and control solution because you don't want to be systematically logging into machines to perform standard tasks, because you realize that if you do that, you mess things up. And I mean, you start also using a configuration management tool because you can't be doing all this configuration by hand, right? So if we take a step back and look at what you've been building, you're ticking all the right boxes. If you look at what the industry tells you that you should be doing, you're doing CI, you have infrastructure as code, your team is DevOps. It's all good, right? But if we take a closer look, most likely your resource utilization on machines is very low. Like you're on average at 20% of CPU consumption, and that's the same for RAM. But you still have these peaks that you cannot accommodate, which you shouldn't, because overall most of your machines are underutilized. And these peaks, they happen on very specific parts of your infrastructure, such as like the web serving front end or the batch machines when you run your analytics. Adding new services or components in your infrastructure, it becomes exponentially harder. It doesn't logically follow that the one repo in your infrastructure that has the most activity should be your configuration management one. Maybe you should be spending more time developing your product. And you're constantly, every time a new component comes in on your infrastructure, you have to make allocation decisions. You have to figure out, where should I be putting this part of my infrastructure? On what machine can I maybe co-locate this to increase consumption? And handling failures is hard because you have a monitoring system, hopefully it's Riemann, and it tells you when things break, but it doesn't fix things for you. So you have to shuffle services around and make another allocation decision to bring your service back in its nominal state. But from a service point of view, like your split makes sense. You have platforms with products. You have a product platform where there's your website, your API, your backend, a data platform which hosts your persistence layer with SQL, maybe Hadoop or Spark, Elasticsearch, whatever. A monitoring one where all your centralized logging solutions, your monitoring and telemetry storage is there, and then like infrastructure support services such as your CI infrastructure, your command and control and configuration management. So it does make sense, right? And what you would expect from a system is have the ability to just spread these platforms across your machines and have the ability to accommodate for peaks by shifting allocation dynamically, right? So you start looking into alternatives, and right now, if we look at the landscape, there's the building blocks, which are containers, which gives you a more lightweight and malleable unit of isolation for processes. Private paths, which brings its own set of constraints and forces you to fit within like the constraint of the past, which I won't talk about today, and cluster allocators, which I've come here to talk about. And specifically, what I'm trying to get at is that it's not your job to be shuffling stuff around, right? And to be making allocation decisions. So how do you get out of that job? Mesos is one of the answers, and I'll try to convince you that it's a good one. If we look at what it says on the box on the website, it says that it abstracts CPU memory, storage, and other compute resources away from machines, may be they're physical or virtual, and that enables fault-tolerant and elastic distributed systems to be easily built, and run. If we dive a bit deeper, it has this three-component architecture where there are masters and slaves using the Mesos terminology, and scheduler that come in that you write or that you pick up from vendors, and then that sit on top of Mesos. Zookeeper is used for coordination, but that's a bit of a detail. If we look at how it works, the masters, they coordinate, slaves expose resources, and workloads come and sit on top. Masters, the responsibility that they have is that they expose an HTTP and protobuf API, a web UI as well to give you some insight into the system. They're the main entry points for frameworks, and most of what they do is gathering capacity information from slaves and presenting that to frameworks. Of course, it's built in a highly available manner and lets you scale horizontally to a rather large set of nodes. Slaves using the Mesos terminology are used to launch tasks. Tasks are isolated as containers, either Docker or plain C group namespaces, and I'll come back to that. And they expose resources to their master. And resources may be CPU, RAM, IPs, volumes, attributes, or labels. So frameworks is what you build or what you pick up from vendors. They instrument workload. So Mesos in and of itself doesn't do anything. It waits for frameworks to tell it what to do. And frameworks are built with two components, a scheduler and executors. Schedulers, they connect to a master, they receive offers, they receive resource offers, and they decide to pick them up or not. When they pick them up, they can use them to launch tasks, and again, tasks are isolated processes. If you have services to expose, for instance, if you were to run an HTTP service as a Mesos framework, the scheduler will also be responsible for exposing HTTP ports. And executors, they're optional. Mesos is able to start tasks as Docker containers again just by itself. But if you have an executor, it will be responsible for interacting with the scheduler. Messages can be sent, task statuses can be sent, and reported to the scheduler. Again, that's the architecture we end up with. It's rather lightweight in the sense that most of Mesos are C++ processes, rather lightweight, interacts with the Zookeeper, but most of large infrastructure already have some Zookeeper running for a purpose of another. So usually it's not too high of a cost to bring it to your infrastructure. Let's talk a little bit more about the allocation-based model, the offer-based allocation model, sorry. So again, the scheduler receives the list of offers, such as I have this and that CPU capacity available, that much RAM available. The scheduler decides which host it wants to run the task on, which offer it wants to pick up, right? The master does decide which resource to offer to schedulers. That's something that's pluggable, this allocation decision, but the default one in Mesos is rather efficient. It does put a lot of responsibility on the scheduler, since you're the one making allocation decisions. Mesos tasks, they're run in a container. Docker is supported, and I'm sure most of you know about it. The other option is plain Linux namespaces, so cgroups, which is the foundation on which Docker is built. Additionally, Mesos tasks, they may provide a health check to let the masters know if they're performing their service adequately. They may ask for things such as port forwards or ask for persistent storage volume, which is interesting because it allows you to build also your persistent layer within Mesos, which usually isn't the case for cluster allocation type products. All right, if we look at the frameworks that already exist, Spark is the original one because that's what Mesos was initially built for, to run Spark. Marathon and Aurora are private paths with a bit more flexibility type frameworks. Chronos is like a distributed cron. Jenkins has a way of using your Mesos cluster to distribute the slave workloads. And then there are a few persistent layer type solutions such as Hadoop, Kafka, and Cassandra that know how to run on top of Mesos. There's even a MySQL one now, which is a bit young, which is why I didn't mention it. All right. So that's all good. The basics are there. It's easy for you to come in and write a scheduler and then run it on top of Mesos. What I want to spend some time on now is showing how Clojure can help make this simple using a library that we built that's called Mathematic. So it's two simple artifacts, a plain one and one that exposes an asynchronous facade. Why did we build a library and not a framework in the first place? We started off by building a framework, and Mathematic are bits that we extracted from this because we figured out that we would be building several frameworks and that there's like a common set of things that you want to do, that you always want to do when building frameworks, and it might be interesting to have that available as a library to make some workload generation easier. And you might have, you might feel that the existing frameworks don't exactly fit your needs. And yeah, again, when you're building as a service type products, where when customers come in, you need to allocate specific resources from them. Tying that into Mesos is something that's interesting, and that's definitely something that we leverage. All right, so the components of the library, Clojure types for Mesos data structure, which are usually protobuf. Just plain facades for creating schedulers and executors, and asynchronous version of the facade, and allocation helpers to help you make decisions that you're usually interested in making. The Clojure type interaction, it's all fits in a single namespace, quite easy, and it's just three functions: protobuf to data, to protobuf, and data to protobuf. It's pretty straightforward what you can do with it. It does avoid you to deal with the pretty clunky protobuf instantiation that the Java libraries usually give you, and you just work with plain maps, which is nice and easy. There are record implementation for each type, but you can also work with just plain Clojure maps if that's your thing. There's an executor and scheduler facade. It's protocol based. Your client code just reifies the protocol. So to reify a protocol in Clojure, it's like implementing an interface in Java for those who are not used to the polens. And you perform side effects with a driver. So you have a protocol to input messages, and you have a driver to output messages. That's what it looks like for the executor. If we look at the ones that are the more interesting, launch task is a message you received when you've been instructed to start something. And framework messages are the scheduler just telling you things. And the only two things that you can do is to send framework message or send status updates. Right, it's the same for the scheduler. Again, two protocols. And here you have a few more messages, resource offers to say that you received new resources, framework message, or status update for a task. And as output, you can launch tasks, kill tasks, reconcile task, which is when you're building HA type solutions or request resources. And that's all it comes down to. Having the ability to getting those resource offers, picking up, making a decision, and then launching a task. That's what a resource looks like. It's just a plain map with a few fields that tell you what's available on a specific host. A task, again, is a plain map where it specifies what type of resources it needs to run and the command that it should be run. That's the case for a C group type task. For a Docker task, you just specify the image that you're interested in running. So again, when you look at it from a Clojure perspective, rather simple maps to express something. And the core async facade, they're an opt-in dependency, and instead of having callbacks, you just have a channel with messages that come in. Which means that you're able, like in very few lines of code, to write a scheduler that inputs all these messages and that dispatches to a handling function and reduces over local immutable state to update its status. And that's almost all you're going to need as a basic structure to write frameworks. That's that approach most of the time. Last part is the allocation helper. It's protocol based. It just given a set of tasks that you want to run. So let's say your wanted workload and a set of offers. It can help you make the allocation decision. There's a single implementation for now called the naive allocator. It does account for things such as the number of instances of a task that you want to run and a collocation factor. Say, because most of the time, if you have 6 processes to provide a service, you might not want more than 2 instances of that process on a single host, just in case that host fails, because they do end up failing at some point. And that's a decision that the naive allocator can help you make. I've been working on a core logic based implementation of the allocator, but it's not in the library yet. Hopefully, I end up managing to do it. So these are just the 2 additional fields, and I'll speed up. If we take a very simple workload such as a distributed cron with static configuration, there are 2 jobs that you want to run, an analytics job and a metering job for your service. The only state that you're going to need is this, the driver to interact with Mesos and a set of already running processes so that you don't have 2 instances of a single job running. Ticking can be done with this. There are plenty of ticking libraries available in Clojure. In this case, I'm using cronj. And you can just put that ticking message on the same channel than the one that you get with Mesos. And again, we're using the same structure as previously. So we're ticking on that channel. We're also receiving Mesos messages on that channel, and we're using the same reduced trick on the channel to process both messages. And that gives you a very simple structure where this channel receives messages from both Mesos and the ticker, helps you produce that state, and with a simple dispatch function, you're able to accept offers, and so you just assoc your offers to your internal states. Handle ticks, you just verify that that there's an already running instance of that job or not. Otherwise, you just use the allocation helper and then start your workload. Updating status info when you're getting back information from Mesos just lets you update your internal states by setting the state in the set of running things, and that's it. That's all you need. what I'll spend a few minutes on now is how some of the Clojure libraries can help you make even better decisions, and which is why we chose Clojure in the first place. I'll handle topology changes, and I'll talk just a little bit about this using a similar approach to what Ohm does in the Clojure script world by using observable atoms and using Clojure data diff and core match. You're able to easily converge to your wanted topology. We just start with the simple atom-backed configuration. So any change in your configuration is swapping an atom and updating its state. Here I just have the pretend watch namespace. And then you use the add watch property of atoms to observe it with a function. The conversion, the topology conversion function is just taking decisions which produce side effects and then performing those side effects on Mesos. And to make those decisions, we use Clojure data diff. So this doesn't work, right? Yeah. Which will give you a set of things that have changed. And when we can map this with Clojure core match to have like a very straightforward layout of the decision process that we want to take. And that's something that I think is very elegant because it maps out what you want to do in a pretty simple way. And you end up with that structure, which is still rather simple, with HTTP and file system input for your configuration, decision process mechanism, and then all this goes into a channel which helps you continuously converge to your expected topology. All right, I had to rush through these things a little bit. Don't hesitate to hit me up for later explanations. To wrap things up, Clojure really helps here. Some of that stuff you could have built in lower level languages, but having these elegant libraries to make decisions help you work in a more efficient manner. Most of that stuff is taken from a framework that's open source, that's called Bundas, also on GitHub. I think the core async help really model the flow of events in a distributed system by having that channel approach. Core match really brings clarity to the whole process. As far as we're concerned, Mesos helped a lot because it removed us from that constant allocation decision process, like manual allocation decision process, easy, highly available and fault tolerance features. And as the ops burden is greatly reduced. Just a few words on the future work that we'll be putting into this. We're happy to onboard new contributors to Mathematic and Bundas. We're following Mesos releases closely. I'd like to finish the core logic implementation of the allocator, and publishing example frameworks is definitely something we're wanting to do. And that's all I have. Thank you very much, and I'll be ready to take questions. I have to say I planned for 40 minutes, so I had to rush through the core match thing. Sorry about that.
So this is an Apache project, which tends to be a Java sort of JVM ecosystem. So how tied into Java is all of this, or could you use it with any sort of service?
So it's not tied to Java at all. Like
okay.
Mesos itself is C++ only.
Ah, okay.
So it's as long as you're able to. It's tied to Zookeeper as well, in a sense. But no, as long as you're able to write to HTTP and protobuf, it's all right. The protocol itself, like the way it's implemented, is a bit quirky. And the next major version of Mesos will have something that's a much more easily implemented in other languages. Like right now, most of the client libraries tie into the C++ client library and use that. But from Julia, for instance, it'd be quite easy to tie into it. As long as you're able to bind to a C++ library, you're fine.
there seems to be quite a lot of overlap with Kubernetes in this area. When should I choose to use Mesos versus Kubernetes and vice versa?
I don't think you should choose between the two. Kubernetes also is able to work as a Mesos framework. So having the resource allocation and distribution handled by Mesos and the pod abstraction provided by Kubernetes is actually something that's quite valuable, I think. All right, thanks a lot.